So thanks for the great introduction. I don't have to tell anything more about me. My name is Mehmet Soysal. I'm working at the KIT, and I'm presenting our experience and work that we are doing with the on-demand file systems in our HPC environment. First, I'm going to give a brief introduction into the motivation and the background while we are using on-demand file systems. And then I'm showing how an on-demand file system can be integrated into an HPC batch system. Then some generic benchmarks are shown. And after the benchmarks, some real use cases from our users that are using on-demand file system on our clusters. And at the end, I will conclude with a summary and conclusion. So first, why this everything? So everything started with the DFG project. That was a small project within the SPEXA. That was the priority program software for exascale computing from the DFG. And together with Mainz, Dresden, and of course, we at the KIT, we were tackling the I/O bottleneck of HPC systems. And one important point was that we made use of on-demand file systems. So that was one of the main ideas of that project. In addition to this, we at KIT always had traditional node local storage. In the past, we also had spinning disk in the compute nodes. Then just SSDs emerged into the system, and today we are having NVMe SSDs in every compute node at our site. And what we also had since as long as I'm working here, we have some use cases which do a lot of I/O, and then we needed a solution to handle this heavy I/O use cases until they are optimized, or until we can, together with the user, optimize these use cases. So we needed something that we can just immediately use, or just enforce the users to use it, that we get rid of this heavy I/O. So as an example for our systems, I just have pointed here two of our clusters, the ForHLR2 that went online 2016 and went out of operation beginning of this year. Every compute node had a 400 gigabyte SATA SSD in it, around 500 megabytes read-write performance per SSD. Our new system, Horeka, that went online this year, there we have every compute node equipped with a terabyte NVMe SSD. So the read performance is around 3 gigabytes per second, and the write performance is around 1 gigabyte per second per node, per compute node. So next, I would like to introduce the integration into an HPC system. But before I start, I'm mentioning always what an on-demand file is. I want to explain the basic concept for everyone that not heard anything about that. So how that on-demand file system works. Here we have the current usage of an HPC file system without an on-demand file system. Here we have two jobs, job 1, job 2, and each of them has 3 nodes allocated. Each of the nodes has a node local SSD, but usually the application is not using that node local SSD. It's writing directly to the global file system, probably from every node or even every task, and doing some weird random read writes and so on. With an on-demand file system, the idea is that we create for every job a private on-demand file system that is only accessible and visible from the allocated resources of a job. And as storage for this on-demand file system, we use these node local SSDs. And so that the application should use that on-demand file system during its execution. And after the job has finished, the data is staged back to the global file system. So this is the basic idea on how we want to make use of on-demand file systems on our system. So, for as on-demand file system, we use BeeGFS. And especially the tool Beyond, that is just as a tool to set up BeeGFS on demand. And that's what we are at the moment using for production usage on our systems. Other file systems are planned, especially GeckoFS, which is a very good candidate and offers a lot of metadata performance. So, and of course, the on-demand file system is only on demand. So first, it should be made minimal changes to the system usage, and this on-demand file system should only be started when a job is requested. We just made it available with a flag on job submission. It's just called constraint beyond. Oops, I'm sorry. So, and then the system knows, or the resource manager, when it should start an on-demand file system. So we are using on-demand file system since many, many years, and we have different implementations. In the beginning, we had, while we used Moab as a scheduler together with Slurm, we extended the data staging feature of Moab. Another implementation, this was just basically proof of concept, was extending the burst buffer plugin of Slurm. And what we are actually using at the moment is just the modification of the prolog and epilog, but I will show that in more detail. What I would also want to mention is that we're using a loopback device as storage for this, for BeeGFS. So the BeeGFS is not writing directly to the local file system like TEM. It is using this loopback layer, and I'm going to explain later in detail why we are doing this. So let's go. This is the most simple version. So we have here the scheduler, and on top of the resource manager that runs on the compute nodes. From the job queue, the scheduler allocates resources to a job and then is going and then initiates on the resource manager that the job prolog is started. And here, the on-demand file system is started, then the user job is executed, and in the job epilog, we just stop the on-demand file system. So the scheduler is not really aware of that the job is requesting an on-demand file system. For him, it is just an arbitrary flag. He doesn't understand really what is going on. And the resource manager is doing the creation of and stopping of this on-demand file system. This solution is very simple to integrate and very reliable, but there is no kind of data staging. So the user has to move data within his job script. But this is what we actually use in our system. So next is the Slurm burst buffer. I'm not sure if everyone knows what this burst buffer plugin can do. It is a plugin for Slurm that is mainly developed to make use of this great data warp nodes which are dedicated storage nodes within the cluster. And that's a little bit different of the concept of an on-demand file system. But as a bachelor thesis, we had a student working on it, and he developed even a pretty useful, or it was running solution, which just extended that namespace of this burst buffer. And when submitting a job and requesting a burst buffer, some nodes were reserved by the scheduler. And on this reserved nodes, an on-demand file system were started and data were staged in. And in the job epilog, after the job epilog, this on-demand file system, the data was staged out, on-demand file system was stopped, and this burst buffer was removed. So as mentioned here, it was only the proof of concept, and we never used it in our production system. So the last one that we used at first, Moab is offering a data staging feature. So where on job submission, data staging is requested, it splits up in 3 jobs. So it's a data stage in job, the payload job of the user, and at the end, a job is started where the data on this file system is just copied back to the global file system. And it has a special feature to accomplish that. It can inherit resources. So once for a job, nodes or resources are allocated, it can inherit these resources for another job. And this is a nice feature that I'm missing on other schedulers. With this, there could be much more done regarding to on-demand file systems. But we used that during our Moab setup. But since we are not using Moab anymore, this is and legacy setup. So, like mentioned before, we are not as a storage for the in-demand file system. We are not directly using the local disk like temp down here. What we do is just we create a loopback device. So how we are doing this? So first, we create an image file with DD and create a file system into that image file. And then we are just loopback mounting it on a virtual directory. And this on the storage team is using this loopback device. So why we are doing this? The first most important why I started this was we needed a way to control how much storage is available for this on-demand file system, and that the user not accidentally just writing up the node local storage. If you do not have a separate partition for temp, for example, it can happen when the user fills up this on-demand file system. It also fills up the disk of the compute nodes. And with specifying a size for this image file system, you have a very good control on it. And of course, you can run any kind of file system in that image file. We are using XFS that recommended from the BeeGFS wiki. Also, you can imagine using ZFS, compression-enabled things, and so on. So, and for stopping that file system, it's rather simple, because instead of removing this millions of chunk files that can be created when using a parallel file system, we have just to remove that image file. And what I noticed during usage is that we get a very good speed boost when using this loopback device, especially for small files. And this is also known, or other people also experience that when using loopback devices, that network parallel file systems can get a speed boost with it. So, so the summary for the integration into an HPC system is, from my experience, the simple solution is usually the best. Just starting and stopping the bottleneck epilog. There were other ideas that you can run multiple storage targets per node. In my experience, just one storage target per node is sufficient. I really recommend using this idea with this loopback device as storage target. And what I didn't show it, but what we are doing in our setup is that we just pre-create directories with different stripe settings. So that we have pre-created folders in that on-demand file system with a small stripe size or stripe count 1 and up to stripe count 32. And that just covers the most use cases that we had on our system. So next, I would like to show some generic benchmarks. These include the start and stop time, the read and write throughput that we can achieve with an on-demand file system. One very important point, even more important than the bandwidth, is the metadata performance, especially when using multiple metadata servers. And at the end, I would like to show how topology awareness can be achieved with BeeGFS. So first, the start and shutdown times of BeeGFS. So the results in this table above are the results when using this beyond script with PDSH. So PDSH is already a little bit faster than using the serial way. But on 256 nodes, if you do not modify the script, you're on a startup a little bit more than 220 seconds. And if you do a clean shutdown, you're around 80 seconds. Okay, that's probably too long for very short jobs. Think of when you have jobs running less than a minute, that doesn't make sense. But we didn't saw large parallel jobs that running that short. So the startup times is okay for us. But it can be optimized. So there is a mail in this BeeGFS user group. It is possible. There is a serial section of that startup script. So if you parallelize that, we were able to start within a minute on 250 nodes, and this is fast enough for our use cases. What I should also mention, what is in the table is a clean shutdown. So since it's in the prologue, in the epilog, that we do not care and want to get rid as fast as possible, there is a very nice option to stop beyond. It's called stop local. This can be executed on every node. It's just ignoring the clean shutdown and stops beyond within seconds. So that's the good part. That's fast enough for us, and there were no need on our side to optimize that further. So next is the read-write throughput that we achieved on our old ForHLR with SSDs and Horeka with the NVMEs. It's not a comparison which is faster, it's just what we could reach on the systems. So on the x-axis, we have the number of nodes from 4 up to 256. The y-axis is throughput, the read-write throughput in gigabytes per second. So the bottom two lines are the measured read and write throughput for the ForHLR using SSDs, scales pretty well. The top line is what we get on our Horeka, and especially I added here the numbers for the NVMe read, and I couldn't see any problems on the read. If you look on the right, that yellow line, it just drops a little bit, but still way more than we will ever need on our system. So it scales pretty well. Something more important from my experience is more important than bandwidth is the metadata performance. Here I picked up some values I received from an MD test benchmark running on 16 nodes. The blue bar is when we only use one metadata server. Orange is when we use 4 metadata server on the 16 nodes, and gray is when we use 1 metadata server on every node. So in total, 16 metadata server. And you see, we get a good scaling. It's not linear scaling like we expected. If you want that relative values, I have a slide in the back in the backup slides. So it's better readable probably, but I wanted to show you the absolute values that we can achieve. What I also should mention or would like to mention is that this benchmark is run with MD test, and every task that is doing operations is working in its own directory. So this is very helpful for the performance. And if every task put in the same directory, the values are very low and you don't get the performance out of it. So here at last, I want to present something about topology awareness. So on ForHLR and Horeka, we have a fully non-blocking interconnect. But what if you do not have a fully non-blocking interconnect? For example, very large systems have a weaker interconnect. It's of course they have in total it's a better, but imagine of a Dragonfly or Tofu network, or like that system in Stuttgart with this hypercube. So the global has some blocking factors in it. And of course, a fully non-blocking interconnect is very expensive. And some people don't need that, so they want to save money on that. Additional to that is that BeeGFS offers storage pools. So the idea was, can we use these storage pools for topology awareness? So first, I need then to explain a little bit the topology that we used in our environment. So here we have the small island on our ForHLR2. So we have here the 2 switching levels, 6 core or root switches. Below that, we have 14 leaf switches. And on every leaf switch, we have 24 nodes. So the nodes have an uplink of 56 gigabyte per node. And every leaf switch has 12 100 gigabits to the core level. It's not exactly full non-blocking. If you calculate it, it's something like 1 to 1.1. But in our case, we can just claim that it's a fully non-blocking network. So what we have done now. So here down there, we have the compute nodes. We created an on-demand file system across all of the leaf switches. And then we configured a storage pool for every leaf switch. So the idea is when one of these compute nodes is writing to the right storage pool, it stays within the leaf switch and does not do any kind of global communication. And what I just indicate here with the red crosses, we configured an on-demand file system with the storage pools, and then we turned off a few of these root switches to create an artificial bottleneck in the network. And then see how that storage pools have an impact on the performance. And here are the results for the write throughput. This benchmark was, like mentioned before, on ForHLR2 using 240 nodes. The red line here is the maximum SSD write throughput that we could get theoretically. The blue bars are the results without storage pools. The orange bars is when using storage pool. On the x-axis is the number of active root switches. Here, the first pair is when all 6 root switches are active. Here we have 3 turned off, so 3 root switches are active, and here just 1 switch was left active. You can see how the throughput without storage pools, so the blue bars, drop below the artificial bottleneck, which is represented by this black line here. When using storage pools, we almost get the maximum performance out of it. So we can use storage pools. It's a few parallel file systems offer storage pools, and if we just make them a little bit corresponding to the network, we can get incredible write performance and then read performance out of it. So let's sum it up. What I have shown, BeeGFS scales very well. Bandwidth scales almost linear. The NDMS performance scales a little bit with multiple metadata servers. From my experience, what I could observe is that BeeGFS has the same weakness like Lustre. First, it's of course the metadata server bottleneck. If you're just running one metadata server, this is the limiting factor and it's the bottleneck of the whole file system. When multiple tasks are working the same directory, you also get the slow performance. And like on Lustre, you need to choose the right stripe sizes and stripe counts. If you choose the wrong stripe size and counts, you even drop below the performance of the global file system sometimes. That's something that you have to find out with the user and his application. Some specific point about when switching to an on-demand file system is that you have to care about the file size, the stripe count, and on OST storage target capacity. So usually on global file systems, one of the storage targets is very large, so you can store a large file into it. But when using on-demand, the maximum storage capacity in our setup is always 1 local SSD. And if you create a very large file, probably larger than a terabyte, it can happen that one of the storage targets is written full, and then the whole file system just crashes. So the first thing I always ask the users, what is the largest file size that he's using? And if it's too large, I always recommend going for a higher stripe count to not stumble over that issue. So next, I want to show a few use cases that are actively using we're actively using the on-demand file system on our system. So the first one is OpenFOAM. That use case was using 240 nodes, 20 cores. And what is pretty interesting is on every snapshot the user does, 450,000 files are written and a little bit more than 100 gigabytes per snapshot. The second application is Nastia. It's a parallel stencil code solver. This was also executed on 240 nodes. And what it does, it creates per core 1 file, and each file is 1 megabyte large. So it's 4,800 files and 4,800 megabytes per snapshot in this setup. The third one is called Flaps. It's basically a dynamic particle swarm optimization. It does some machine learning and deep learning methods on the results on Chromex and tries to optimize the input or the setup options. So this case is using 50 nodes, and what I can tell it's heavy metadata operations. but I'm going to show in detail. So these were use cases that I just picked over the last years and were actively used in our system, or let's say were used at that time. We picked those use cases because of the problems that they cause in our system. So you might ask, what was the problem here? And trying to explain that here a little bit. So here's the Unix load on our file system, on our Lustre file system, when this OpenFOAM use case, for example, was executed. So we run that OpenFOAM use case 5 times for around a half hour. We wanted just to verify that this is the application that is causing the problem here. So here on the right side in this picture, you see the load, the Unix load of our file systems. The brown line is the average on our 10 storage servers, and the blue line is the Unix load of our MDS server. And you can see between these runs, that is the usual load on our file system. And every time this single application starts, the whole system is getting laggy. And you probably have experienced that when you open files that it takes a second. And this was just one of these applications that is causing this. But the user might not be interested in the load of the file system, or he doesn't even notice that, or there is no way that he sees that. So the only thing he's interested in if his application is running faster or slower when he's using an on-demand file system. So here we run that application 5 times. The blue line is the average of the execution time. So okay, wait. The upper figure is when we run that use case on the on-demand file system. The bottom is when we run that use case on the global file system. In that case, it was Lustre. So, and here on the x-axis, you have the time steps from 0 to 100. And on the y-axis is the execution time for that application in that time step. And you remember in a few slides ago, where I mentioned that he's writing 500,000 files per snapshot. You see the spikes here. He's doing that snapshot every 5 time step. And every time you see that spike, this application is writing 500,000 files and 100 gigabytes. And just imagine he's doing that 20 times within a half hour. And this is actually a real use case. We talk to the user and he needs to do this. So that's what's happening in our system. What you can see here, the black bars are the deviation, the min and max values for that time step. And you can see that when using an on-demand file system, it takes an average a little bit more time for the application, but the deviation is much, much smaller than here when using the global file system. So this is what we have expected. The application is a little bit slower, but we are not affected on the global file system. Very interesting is the Lustre use case. So here we recorded the same idea. So we recorded also 5 runs of the application. The blue line is the average. And that was a little bit surprising for us. So we double checked if we recorded the real values, and yes. So here on the top, it's again when using an on-demand file system. And here you can see it's basically a straight line with almost no deviation. When using the same use case on the global file system, you can see from 0.02 for each time step up to over 0.1 seconds. There's a very large deviation in the simulation time. And this was very surprising for us. We didn't expect it that this is going to happen like that. So the third use case is a machine learning method that is working on GROMACS results. It is creating, it had created a very high operations per second. And here on the right, you can see what kind of operations. So I just collected a few. The most were stat operations. In the peak, this application created around 100,000 operations per second, metadata operations per second on 50 nodes. And this was the loads, this was the operations that hit our global file system. But we switched, or we enforced the user that she should use an on-demand file system. And what was left, so this operations all hit the on-demand file system. And here, this little spike at the end on 1600, 700 seconds is what the global file system sees of that use case when moving to a global file system. So, and this is just one generation. This is an example for running 2 generations of these flaps. So every generation has a very high metadata operation in the beginning and up to 100,000 seconds. What we realized later is that this is the maximum that we could get from with one metadata server. And then there is a very high computation phase, and then when the second generation starts again, first I/O and then a lot of computation. And here again, this little peak is the data stage out to the global file system. So instead, this both hills hitting the global file system, it's just this little peak at the end. So the summary for the use cases or for the experience that I had with our users was that the effect on the application is hard to predict. Some running slower and some running faster. I didn't find a solution to predict which one will benefit from it in regarding to wall time. From everything that I saw is that the bandwidth that we offer is more than enough. The metadata performance is more important. So it's not the bandwidth that the user needs, they need more metadata performance. The good part is the BeeGFS and the on-demand file system is easy to use for users. There are almost no code changes needed, just pointing to different directories. And the data staging is handled by users if they know how the concept works. They prefer it to do their own data staging. Some are staging at the end and some are staging during the execution of the applications. And what happened in the recent years is that we just enforced some users that they have to use on-demand file system or are not allowed to use our systems at all. So now we are coming to the end. And so the summary and the conclusion about all the years that I worked with this on-demand file systems is BeeGFS is easy to integrate. It has the same advantages and disadvantages like Lustre. Almost the startup time is acceptable for us. But something some people always mention is the SSD wheel leveling. Yeah, it should be observed. In our case, with our use cases, we did not notice any problems so far. But let's see how. Probably in 2 or 3 years, I've got a different point on that, different view on that on our Horeka system. So, like also mentioned, I really recommend using Loopback devices. It improves performance in all cases, especially when using small files. And what I can say is BeeGFS scales well regarding to bandwidth. To metadata performance, it's okay. It could be better. It's not that scaling as well as the bandwidth, but with multiple metadata servers, it's okay. It's better than it's more than we could offer with our global file system. Topology awareness is also possible with storage pools. I've got the issue that I have a solution for a problem that we do not have in our system. So if anyone has a use case that an application is topology aware and doing a lot of I/O, that just let me know. We are looking for a problem that we could solve with that. So like mentioned a minute before, the impact on an application is hard to predict. We need just to try out, let the application run and just take a sharp look onto it. That's at the moment the easiest way to predict if it's how the application behaves with an on-demand file system. As a generic solution or a generic tip from my experiences that I always tell the users, is also in our user docs, that I always tell them, add one additional node to the job. and do not run your application on this additional node, so that the metadata server can use that additional node for his service. When using MPI run, for example, it's quite simple. Just use the option no local, and the node where this MPI run is invoked is just not used. There are no tasks started, and the metadata server can just use that node for his service. Another observation was that the metadata performance is more important than bandwidth. So we added recently the option to request multiple metadata servers. We do not have much experience up to now how that behaves with parallel applications if on every node metadata server is running. We had fancy stuff regarding to data staging. Oh, sorry for the typo. So on our systems, the user handle their data staging on their own, and that's not a problem at all at the moment. They're quite happy that they can run their jobs without any issues. That's more important for them. But what we have shown is that we can do concurrent data staging with minimal interference to the application. It depends on how from which node and which tool you use to stage the data. But what I can say as a final summary is that the advantage of an on-demand file system outweighs any disadvantages. And most important, especially for the operation team, was that we can just reduce the load on our global parallel file system. And that was always the main reason why we enforce users on using an on-demand file system. So thanks for your attention, and I'm happy to answer your questions.
Thanks a lot, Mehmet, for this interesting talk. So if there are any questions from the audience, fire away. Please raise your hand or just unmute.
I have a question. Thank you, Mehmet, for the talk. It was really interesting for me. I have two kinds of questions. The first is when they are both more or less technical questions. The first is the measurements where you turn off the core switches to see the impact of the topology aware pooling. How did you measure that? Did you pull the cables from the switches, or did you have some software defined way to do that?
Yeah, so I can tell. I see also Richard Walter here in the chat. So we checked that they were unmanaged switches, and I was looking for a solution to disable routes, and then Richard just asked me if I have the whole small island reserved for me, and then he had the brilliant idea just to pull the cables. We just pulled the power cords, and they were offline. So we are pretty sure that they were not being used.
Yeah.
Thanks to Richard, I was looking for many hours how to route something in the InfiniBand network, and it's quite hard, honestly. And he had the brilliant idea just to pull the power cords.
Okay, thank you. Yeah, that's a solid solution. Because I also looked into this routing stuff, and it was really difficult to make some assumptions or some predictions based on that. Just looking from a software side on it.
Mm-hmm.
And the second is this option with multiple metadata server. Did you add this to Beyond? Because to the best of my knowledge, I have no options when I set up a Beyond file system to control the number of metadata servers that they use. Or did I miss something?
Probably you missed that point. It's I'm not 100% sure. I have to take a quick look. It's the option -M, if I'm not wrong. That's where you just tell the number of nodes. of the metadata server. So the first in the node list, the first numbers or first number that you define is so there's an additional metadata server started.
Okay,
It's an option.
Then it's just not documented on the BeeGFS side.
I'm not sure, but I found it quickly. So the main problem is that we have to check if this is doing any harm to the application. At the moment, only a storage daemon is running on the compute nodes, on the most compute nodes, but metadata server is very CPU intensive daemon. So
yes,
it could harm more than you could benefit. So
and it's also memory intensive, so
yes,
it uses a lot of main memory.
That's right. So we need to do a little bit more evaluation on that. We have just recently added that option and offering that, and hoping that some users that we get some experience with that.
Yeah, that's really cool. Thank you.
Okay.
There's a question in the chat by Marcus Boden. Sorry. Can you share the Pro-Epilog or burst buffer scripts for Slurm integration?
Sure. It's there even somewhere available on GitHub. I can probably put that in the slide. I have multiple versions even on the Prolog and Epilog, depending on the site. So I also have written some Prolog Epilog scripts for other sites so that they can integrate it. It just depends on your flavor, how your Epilog looks like. Some have a very long script. Some have some init day style, like, you know, numbered and multiple. I can just add it to the slide. They're available somewhere online on GitHub. I published them, but it's not hard to integrate it in your Prolog Epilog.
If you could add a link to the slides, and then we will publish the slides.
I'll just add a link to the slides.
That would be perfect. I have a question. What about interoperability with MPI-IO? So can you use MPI-IO on the on-demand file system? Yes,
that was the reason why we are using BeeGFS on production. So just imagine everything that you can do on the global, like Lustre, it also performs pretty well on BeeGFS. So we didn't have any use case that didn't work with BeeGFS. So if someone is doing, of course, a very good MPI-IO, writing and reading files, we also benefit of that. BeeGFS will also benefit. So I didn't encounter any problem, or I didn't notice that any user had a problem. So when the application runs on our global file system, it should also run on BeeGFS. Up to now, you never know.
And in order to influence the striping, you said you pre-created different subdirectories.
Yeah.
But could you also do that from MPI with info objects?
No.
Okay.
Honestly, not.
Okay.
We didn't have that problem up until now.
All right. Any more questions? Okay.
Yeah, Marcus here. I have one more follow-up question regarding Slurm. Which burst buffer? I guess you used the older burst buffer plugin, right? Because there has been a new version of Slurm that has completely reworked the burst buffer plugin, which might be interesting for you if you don't know that.
Oh, thanks for the information. Honestly, I didn't know that there is a rewrite. It was a few years ago that we just extended the burst buffer plugin. We didn't publish it. It was just a bachelor thesis that you can find online, but it was only a proof of concept. Can you say what has changed in this burst buffer plugin?
I think they made the generic burst buffer plugin actually usable. So they have. I have looked into it, but not used it yet by now, so I can't really give you any details. But it's quite well documented right now on the Slurm homepage.
Yeah, right. Because there was this generic plugin, a generic burst buffer that was almost no code or not even.
Yeah, that
filled.
was useless.
and then there was this data warp that was the only thing that was implemented, and the student just implemented this generic ODFS namespace where he just doing that resource reservation, that's on-demand file system startup and this data staging into it. But nice to know that they finally decided to implement a generic solution or generic
I think
version.
they even try not to go for it's still called burst buffer, but it's actually more for staging in general. So they didn't have a better name. You can use it for anything according to scheduling.
Good to know. But as I mentioned, our users, so we realized that our users are not very interested in this automatic staging. They do that on their own and they know much better. So a generic solution for all of our users, I'm seeing that could be hard, especially when you want to do the staging and all that stuff. If you just explain to users that they have to make sure that their data is copied back right in time to the global file system, they will take care of it. So luckily, we have very skilled users on that level.
Lucky you.
Yeah.